So welcome to the lectures of the elementary principles of the chemical processes. It's going to be the end of this course. I hope you already learned something from this course. I do really hope. So anyway, so let's have a quick recap about what we learned on Monday. Monday, we go to section 6.6, which is equilibrium between two liquid phases. Remember? And this topic is not new for you because you already learned this topic on chapter 4. And we did midterm exam with this one of these question in your midterm exam, right? Okay, so but anyway, the first one is that we learn is called miscibility. Okay, miscibility. What is miscibility? Miscibility is that there are three types of miscibility divided into three types. The first one is miscible, right? Miscible. For example, water and ethanol is miscible. So it looks you cannot tell which part is water, which part is ethanol. So this is what we call miscible. The second one is called partial mixable. For example, this is one of the case is water and MIBK. So there are two phases, but one phase is not pure component, which is a combination of a component. For example, MIBK, there are two phases. So for example, this is MIBK base or MIBK rich phase. And water probably only 2 or 3% or 5%, for example. And this will be water-rich phase. And the MIBK in this phase is only 3, 4, 5%, something like this. Okay, so this is what we call partial mixable. And the last one is immiscible. Immiscible is one of the cases is water diethylene ether. So these two cannot be mixed very well. You will have a distinct one layers between two phases. Okay, so this is what we call mixability. And after that, we learn liquid extraction, and we introduce you. This is called ABS system. A is feed solvent, B is solute, S is extract solvent. So actually it's S get B away from A. Okay, so B will be taken away by S from A. So A and B is mixable, or is miscible. But A and S is not mixable. It can be partially mixable. But B and S is mixable. Okay, so this is what we call ABS system. So extraction is like this. You learn this, I already showed you a video. So you have AB system, you have AB mixture like this. And you pour this into a tank. Or you can, this is a mixer. So AB was poured into this mixer or this tank. And we introduce S. S is extraction solvent, right? We introduce S into this mixer. And after well mixing within A and B and S, B will be mixable with S. So, and we put this solution into a settler. Settler means that we pour all the liquid into this settler for a period of time, and so it will become two phases. Okay, so in a case So you become two phases. And then after that, you release from the bottom, and this will be, it can be S rich phase, right? And after that, you take away from others, that will be A rich phase. So this A rich phase and S rich phase. Okay? So this is liquid extraction, and we show you an example, which is water acetone chloroform. It can be water acetone MIBK, remember? So acetone is mixable with water and also with the chloroform. So chloroform will take acetone away from water, and we do this process. Okay. And because this is what we know, is what I just told you is what it means the qualitative. How about quantitative? Quantitative means that you need to know how much acetone in chloroform, how much acetone in water. So this is what we call distribution coefficient. We use K to represent distribution coefficient. And another name for the distribution coefficient is called partition ratio. And this is the equation. It's very simple. It means that how many acetone in chloroform, right? And then divided by how many acetone in water. We use a mass fraction. And you can check K from a table. For example, it depends on the different temperatures. For example, 25 Celsius, 50 Celsius, you can get different K. So you can get a K from table, and this is one of the number, 1.72. And I hope you remember on Monday, I told you that the K must be greater than 1. Otherwise, it doesn't make any sense if you want to take acetone away from chloroform, right? It's better to be greater than 1. Okay? So this is called distribution coefficient. Okay, and finally, and most importantly, is we learn phase diagrams for ternary system. Ternary system is, we can regard ternary system as an ABS system because there are 3 components. Ternary means 3, right? 3. Okay? So remember this triangle diagram. This triangle diagram tells us many information, and I'm going to use an example to let you work with me to learn how it works, how to get this. But on Monday, the end of last 10 minutes on Monday, I already introduced this to you, and today we will have an example. Okay, so this phase diagram for the ternary system, and then this part, remember this part is single phase region. This part is single phase region. Okay, single part region, and this part is, so we want, if we have a point around in this region, and we can tell the compositions of the A, B, and S. Okay, the composition of A, B, and S. So for example, I address a point here, and you can see that this is water, acetone, MIBK. So water, there's a number here, water for number, there's a number here for acetone, there's a number here for MIBK. So we are going to do a practice today. Okay, so this is single phase liquid region. Okay, and then another region is called region B, right? And actually this is two-phase liquid region. Okay, and two-phase liquid region, also we also want to know overall ABS composition. So when you address one point here, you also can find out the overall composition. For example, there are 2 phases, right? So, but in these 2 phases, you can know the overall composition of A, B, and S. However, if you want to know the individual phase, the composition in individual phase, for example, I want to know the composition in this phase, or I want to know the composition in this phase, we want to use timeline. We need to use timeline. So for example, if I have a point here, and I know the overall composition for this mixture, two-phase mixture, and then not only I will get information about the overall composition, but also by the time line, this is called time line, we will know water-rich composition, and for the A, B, and S, and also this time line here and time line go to this part, and this is MIBK. So this is MIBK rich phase, and we will know the composition of the A, B, and S. So this is what we learned on Monday, and we are going to do a practice today. So I hope you still remember. Oh no. What happened? Let me close this first. Okay. So I want to show you, I want to use this example and then to practice with you again. And then after that we move to another example. So this is specifying a wave fraction of acetone is 0.25 in MIBK rich phase. And fix both of the phase on the composition of the water in water rich at 25 Celsius. What does this mean? In this case, we already know MIBK rich phase is 25. They are 25% of the. For example, this is MIBK phase, and inside there's a 25% acetone. And you need to know what's the rate, what's the composition of MIBK and what's the composition of the water, right? And once you find out this, you want to know the water rich phase of the and you want to know the composition of water, acetone, and MIBK. Okay, so this is the example you need to get. You need to get some answers for this example. So the 25 where the acetone is 20. So this is acetone, right? So they are 25. So this is 25. 25. So once you go to 25, and because this is MIBK rich, right? So you need to move to the time line. 25 here, right? I want to give you a hint. Early bird, okay, early bird, okay. This is 25 here, and so obviously the time line should be this one because 25 here, right? So this is, you might say, well, why, Professor? This is not the time line. Why this is not the point? Because this is water rich. For time line for the water, this is the point for the water rich phase. So this 25 here, this one is the MIBK rich phase. So the tag tells us this is MIBK rich phase. So this is here, 25 here. And you understand this is the end point of the time line. So where is the time line? Time line is this one, right? 25, so this time line is this one. Okay, so this point represents the composition of the water-rich phase, and this point represents the composition of the MIBK-rich phase. Okay, so let me show you this. So you have time line. You go to this point, this one. So this is MIBK-rich phase. Okay, so what's the composition in MIBK-rich phase? Water, how many percentage? What's the percent? 5%, right? Very good. Very good. Excellent. Okay, how about MIBK, acetone? Acetone 25, right? How about MIBK? 70, right? Good, excellent. So you understand the MIBK rich phase will be, you have two phases. One phase is MIBK rich phase, and you already got the answer, 5%, 25, 70. Okay, and how about the water rich phase? So this time line, so let's go the time line to this point here. So again, we start from water. Water, how many percent here? That'll be between 80 to 85, right? 80 to 85. Let's say 83 or 82, something like this. Okay, so you phase to the 80 water. How about the MIBK? How about acetone? Acetone will be 15, around 15, right? So here is 16. Okay, acetone. And how about so this is this phase to acetone here, and how about MIBK? MIBK is less than 5, right? Because this line is 5, this line is 0, and this point between 0 to 5, so it's about 2, 3 or 2. Okay, but anyway, this need to get together to become 100, right? Because this is mass fraction. You got the fraction all together, water, acetone, MIBK need to be 100. Okay? Right, so this is an example. I hope you learn this is easy. Right, so now let's move to example 6.6-2, extraction of acetone from water. Use the phase diagram. Right, so let's start to work on this together. 1,000 kilograms of a 30% solution of acetone in water. What does that mean? So there are 30% acetone, that means another 70% is water, right? And it's totally 1,000 kilograms. So 1,000 kilograms here, and you have 30% acetone. This is mass fraction, so it's kilogram. Okay, and then 70% is water. So you have 70% by weight of the water. Okay, so you fill out all the information for the first sentence, right? From 1,000 and to here. Okay, and let's move. The mixture is then fed to a settler where two phases form and are withdrawn separately at 25 Celsius. So that means that this was 25 Celsius. Okay, so this was fed into this mixer and then to a settler, and this is 25 Celsius. So 25 Celsius is that you can use that triangle diagram, right? So the question is that how much MIBK must be fed to the process to reduce the acetone concentration in the water-rich phase to 5%. So the question is, if you look at this mixer, and this is 30%, and after that you want to reduce this 30 to become 5%, and then the question is how much MIBK you need to feed to the mixer in order to get extraction and to let this settler have a 5% here. Why? Because after mixing, you go to the settler, it becomes two layers. And the bottom layer, for example, actually is top layer, but anyway, this layer here is, you have 5%, and this is water-rich phase, MIBK-rich phase. So water-rich phase, you only want 5% only acetone. So the more if you don't feed sufficient amount of the MIBK, you won't get 5%. You might get 7%, 10%. Okay? But if you feed a lot of MIBK, this one might get 2% or 1%, for example. But you spend a lot of you waste a lot of money. Okay? For example, if 2% is too good, okay, and 5% is good enough. So you need to know how much amount of the MIBK required to feed into the mixer. So, and then this needs to be reached to equilibrium. That means assume that the fluid remains the settler long enough for equilibrium to be achieved. Okay, so you know, if you do a mixer and you might have complete only 90%, and you put it to the settler require 1 day to become equilibrium, for example. It become equilibrium, and then you have no time to wait, so it doesn't reach equilibrium. But this example is quite simple because they ask us to just assume this is a reach equilibrium. So this flow chart is originally from the example 6.6-2. So all the information is already provided in this flow chart. For example, this information and this information. But what we don't know is also marked by this example already. So this is MS. MS is what? MS is that how much MIBK, right? MS here. And then the output is called ME and MR. Okay, so you have three unknowns. You have three unknowns in this case. But what you don't know is that, you know, there are some information still required in this case. What else? This is pure MIBK, right? And you already complete this stream, and you complete stream, and you don't need to worry about this one. How about this one? MIBK rich phase. So you know the total amount of the solution, but what you need to know others is what? You want to know the max fraction of MIBK and max fraction of water, and also the max fraction of acetone. For the max fraction of acetone, I mark it not in red color. Others marked in red color because these three unknowns, there are only two independent, right? Only two independent unknowns. So the label I mark in red color means that unknown you need to find out. Okay, so you completed this stream already. How about this stream? There are two more information required, right? So this one is the mole fraction and the mass fraction of MIBK, which I mark in red color, and also the max fraction of the water. I didn't mark in red color because of what? Because these two unknowns only one independent. Because these three get together will be one. So there's only one unknown. So actually, if you want to get the answer of this MS, MR, ME, you also need to find out X1, X2, and Y1. Okay? So there are 6 unknowns. So you need to find out 6 equations. Is it possible? Use phase rule, right? But the important thing is, this is chapter 6. So you need to find out more specifications in order to get this done. Right? Right, so let's go to this phase diagram here. And we understand that this is acetone is 5% in water-rich phase. So this is very similar than the example we just practiced. Okay, 5% in water-rich phase. So water-rich phase, 5%, acetone is 5%, right? So 5% is here. Acetone 5%. And water-rich phase is this part, right? This part. So you can go from 5 to here, right? Right? Okay, so you want to know, because this get equilibrium, so you might be able to get x1, x2, and y1 from this phase diagram. Because I already give you phi here, remember? Okay, if I give you phi here, and then you will see that this is the point, which is the composition in the water-rich phase. So what are the mass fraction of MIBK and the mass fraction of water? Water is what? Between 90 to 95, right? Okay, let's say 93, for example. And the MIBK is 5. How about, acetone is 5. How about MIBK? MIBK is between 0 to 5. So let's say, so this is 93, so let's say 2 then, because this all get together and need to be 100. So water-rich phase is acetone at 5%, which is provided by the example already. And water is 93. Water is 93, so 90, 95, and 93 here. So MIBK will be 2. So 2 is what? 2 is Y1. Y1. Bingo. You already get one unknown. You achieve one unknown, or you obtain one unknown variables. Right. And how about the MIBK rich phase? You might say, wow, Professor, this point doesn't reach to any time line. There's no time line for this point. Remember, I told you that MIBK rich phase, the time line, you can draw your own time line. Because if you have a point here, the time line will be between this time line and this time line, right? So this will be this time line. So you will draw some time line like this. You might say, well, Professor, I'm not happy with this time line. I want to draw something like this to here. Well, it's okay. But if you draw a time line like this, below this pink line, this is too far. This is not correct, right? Okay, so the time line needs to be, when a mix does not fall on the time line, interpolation between the lines is necessary. So this is a quick way to let you get the answer. Don't be too stubborn, right? 固执, right? In no time line, I cannot get any answer. This is not engineering thinking. Okay, the line is necessary to determine the composition of each phase. So the point here is the composition in the MIBK rich phase. So what's the composition here? Again, let's start from water. What's the water? Composition of water. This point is between 0 to 5, right? So let's say 3. Okay? 3. How about MIBK? MIBK will be between 10 to 5, right? And very close to 10, let's say 8 or 9. Okay, and the rest will be what? This MIBK will be between 85 to 90. Let's say 86, something like this. Okay, it's very close anyway. So water is what? Water is x2. MIBK is x1. So bingo, without do any calculation of the input equal to output, you already get these 3 answers: x1, x2, and y1. Why? Because this is equilibrium, phase equilibrium. Remember? Okay. So you don't need to create, there are 6 unknowns, so you don't need to create 6 equations at this point. And using this phase diagram, you already get 3 answers. So you can just get the rest of another 3. Okay, so you have 10, x1, x2, and y1. Okay? Are you with me so far? Okay, good, good. Happy to hear this. So, and now let's write down what we get. So this reach to equilibrium. This reach to equilibrium, and we can use this triangle diagram to get x1, x2, and y1. Right? Obtain x1, x2, and y1. Why? Because the equilibrium. Okay, so there are another 3 unknowns here. 1, 2, 3. So let's say DOF. You have 3 unknowns: MS, ME, and MR. MS, ME, and MR. And then you can create 3 equations. Right? Input, water input equal to, there's 2 input, right? And the 2 output. Okay? This is 2 input and 2 output in this system, right? 2 input and 2 output in this system. And then water input equal to water output. Acetone input equal to acetone output. MIBK input equal to MIBK output. So, I don't want to waste your time. So please, you do practice by yourself, and then MS will be equal to 2,334 kilograms. Okay? Right. So we finish this MIBK, we finish this example. So the end of this topic is that, you know, this is the triangle diagram we learn, and this is called type 1 system. So only one of the binary pairs is mixable. So this one is mixable. For example, water, acetone, MIBK, or arsenic acid. This is one of example. However, you can see another type. You can see another diagram like this. This is type 2. So there are 2 of the binary pairs are immiscible, like this mixable and this one. Okay, and this is one of the example. And we don't have time to introduce this to you, but I think this is enough for you to learn. Okay, and then the summary, I already introduced this to you. So this is for section 6.6 of the chapter 6, which is adsorption on solid surface. So what is adsorption? I just told you that it's related to the solid and liquid, or solid and gas, but mainly we want to know is the solid and the gas. Well, I might be wrong, but anyway. So this is a solid surface here, and you know, this represents molecular. So what is adsorption? So adsorption is the attraction of a chemical species. This is chemical species in gases and or liquid to surface of the solid. This is surface of the solid. Okay, it is the base of a number of the separation processes. So you want to know the amount of the molecules or atoms on the surface. So when this molecule become adsorbed on the surface, this can be regarded as a solid. This can be regarded as a gas or liquid. Okay, so we call it condensation, right? So this is the gases or liquid atoms, and this is the adsorbed species. Okay, so this from gas phase, the species from gas form to become liquid are from the solid form. Okay. So now you know the important thing is the solid. The solid, what we call the solid is adsorbent. Adsorbent. What is adsorbent? Adsorbent is the adsorption operation utilize a solid with extremely high surface areas, because you need to let molecules adsorb on the surface. So you require a huge surface area, right? So it can be 300, it can be 2,000. and cubic meter per grams, okay, of the activated carbon. So this one of the example is activated carbon, 活性炭, right? The 活性炭 has a lot of activated carbon has a lot of surface area, and then taking advantage of the affinity of the specific components in the fluid or for the surface of the solid. The solid is known as an adsorbent. So the adsorbent like this, but if you enlarge of the surface on this kind of adsorbent, you will see a lot of pores, or the surface is not flat. So you can have a lot of surface area. And if you have a lot of surface area, the molecule will be absorbed on the surface. So you can absorb a lot of molecules in the gas phase or in the liquid phase. Okay, this is called adsorbent. So what is adsorbate? I'm sure you know. So one of the examples is, you know, when you play basketball. No, you don't play basketball. The basketball court is about, the surface is 420 square meter. Okay, but you know, for the activated carbon, 1 gram, which is like a very tiny weight, the surface area is about the same size as this basketball court. So the surface area is huge. You know, when I was in United States at Stanford University, I took my two girls, my daughters and my wife to see, you know, that his name is something Curry, right? Steve Curry, is that right? You know that? No? Okay, that's very fun. Oh, see the basketball. Anyway, basketball, football in United States. Anyway, so you can imagine this is a very tiny amount of the adsorbent and create a huge surface area. So you can absorb a lot of materials on the surface. So adsorbate is that the components attracted to the solid surface is an adsorbate. So this is what we call adsorbate. Okay? Okay, so adsorbent can have many type of forms. Like this is kind of padded form, right? This is a powder form, padded and powder. So molecule will attract on the surface of the adsorbent by what? Van der Waals, right? Van der Waals forces. Okay, attraction. So you can find a lot of applications for the adsorption. Okay, so you know, adsorption of the odors. So when you don't smell good, odor is that you don't smell good, right? Something doesn't smell good. You use charcoal in a refrigerator. The refrigerator doesn't smell good. You put the charcoal in. So charcoal will absorb molecules which doesn't smell well, smell good, right? Baking soda. Or you know, in order to get rid of water from this air, you know, the air has a humidity. So you don't like water in the air. So you have a you can use the adsorbent. So air passes through a bed of calcium chloride to remove water vapor. Okay, and then use the activated carbon to do the second process. So calcium chloride to absorb A material, activated carbon to absorb B material. So you can have different steps. Different stage, stage 1, stage 2, stage 3, you can absorb different type of the molecules or atoms. Right, so now, this is important term, we call it adsorption isotherm. Isotherm is 等温线, okay, isotherm. Isotherm means that you keep the process at the same temperature and you measure the differences of the absorption. What happened? It's not earthquake, right? Should we run away? No? Should we stay? I hope there's nothing. Right. So adsorbate equilibrium data on a specific adsorbent are often taken at a specific temperature. Specific temperature means what? Constant temperature. And are referred to as the adsorption isotherm. And the amount of adsorption is what we call Xi star. Star normally means what? Saturated. It reach equilibrium, so we call it saturated. So Xi is the maximum mass of the adsorbate, I species. Okay, that can be held by a unit mass of the adsorbent. And you can use a Ci or Pi. C represent concentration, P represent pressure. Because in the gas phase, you don't use C concentration. You use pressure to represent the concentration. It depends on liquid phase or gas phase. Okay? So C is the concentration of adsorbate in I, adsorbate I in the fluid contacting in the solid. So this is the concentration, right, of the adsorbate in adsorbent. Okay, Pi is the partial pressure. You know, pressure represents the concentration, the amount of concentration in the gas phase. So the partial pressure of the adsorbate I in the fluid contacting the solid. Okay? Right, so how do you determine the isotherm? First one is, for example, you have a carbon tetrachloride, which is CCl4 vapors, and the adiabatic carbon system. So CCl4 shouldn't stay in the gas phase. You don't want to have CCl4, which is the carbon tetrachloride. It's not good for your health. So you want to have adiabatic carbon to adsorb carbon tetrachloride. Okay? So procedure is what? Procedure is you have amount of the adiabatic carbon, which is G0 here. So place a non-mass adiabatic carbon G0 in a chamber whose temperature is controlled at a specific value. So you can, because isotherm is the constant temperature. So for example, temperature at 30 Celsius, and you put a certain amount of the adiabatic carbon in the system, and we call it G0. Okay, and after that, so there's no molecules. You don't introduce carbon tetrachloride into this system. Okay, at this moment, draw a vacuum in the chamber P0 and then admit carbon tetrachloride vapor until the desired pressure P1 is reached. So here is P0. So P0 means what? No pressure. And that means what? No carbon tetrachloride. And after that, you start to introduce carbon tetrachloride into this system. So you see some molecules here. So the pressure becomes P1. Right? And this will reach equilibrium, means what? The carbon tetrachloride absorbed on the surface, and we keep on introduce carbon tetrachloride into this, and in the end you will reach equilibrium. That means what? There's no more, there's no absorption, there's no absorption at all, no absorption, and so this one will stay on the surface, in the gas phase. So you have a P1, and then interestingly, and then in that case, you can measure the G1, right? Why? G1 will greater than G0. Why? Because the molecule will absorb on the surface. So the adiabatic carbon, the weight of the adiabatic carbon will increase because of the absorption. Okay? So you got a G1. And after that, interestingly, you introduce more carbon tetrachloride. So you can see the concentration of the P1 and concentration of P2. P2 were greater than P1. So you got a P2 and you got a G2. So you found out that more carbon tetrachloride were absorbed on the surface of the carbon, activated carbon. And this moment, P2 and G2. So if you want to know the amount of the absorption, and that will be G1 minus G0, right? Or that will be G2 minus G0, right? So you can do P3, P4, P5, P10, right? So this is called equilibrium data for carbon tetrachloride absorbed on the surface, on the activated carbon at 34 Celsius. So this system will keep the temperature at 34 Celsius. Okay. As a result, you can get a table like this. So the pressure P here is 0. You got nothing because there's no air, there's no carbon tetrachloride. Okay? And if the pressure, which is 1.69 millimeter mercury, which is very low, and you got 0.07, Xi will be 0.07. Xi means what? The amount of the carbon tetrachloride absorbed on the activated carbon. Okay, so by the increasing of the pressure, the amount of the absorption, amount of carbon tetrachloride will absorb more on the surface. And you might say, "Well, Professor, something wrong because this is 0.71, 0.71, 0.71." So that means what? No matter how much pressure you increase, this is the maximum. And this is the maximum. So if you plot a curve which use the x-axis as the amount, as the pressure, and y is the amount of the absorption. So you can get a curve like this. You increase the pressure, and then the amount of the absorption will increase, but eventually you will get to reach to a steady state, or you reach to a maximum level. It doesn't increase no more. So how can we read this? So at a low adsorbate partial pressure, isotherm made linear. So this looks like linear. It's a kind of straight line. However, when you go to the higher pressure, so you can draw for this, right? You can write equation like this because this is linear. So you just need a constant related with the concentration or the partial pressure for the very, very initial stage or very, very low pressure. Okay? So how do we find an equation to represent this? Because if we find an equation for this curve, then we can do the prediction in the future. So this is what we call mathematical modeling. So it's important to find a mathematical equation to represent the curve. So that's what we learn. What we learn is called curve fitting of the isotherm. So what do you learn in chapter 2 in this course? You learned this in chapter 2, right? Okay. So curve fitting method. If you have a curve, make it become linear if it's non-linear, right? Okay, so you can have linear fitting method, exponential fitting method, log, polynomial fitting methods. So if you put all the data to a line, this looks like this. It doesn't look good. There's no mathematical equation. But if you use polynomial to represent this, this is the simulation curve. This red line is a simulation curve which is fitting quite well with this data. So you just use 6 polynomial equation, you can represent something like this. Okay. However, we have another one called Langmuir isotherms. Langmuir isotherm is a very well-known equations to use the mathematical model to represent the isotherms. Okay, so this is how this curve represents the Langmuir isotherm. Right. So you might say, well, Professor, I'm not happy. I have my own equation. Yes, please do. Okay, if you can create your own equation, you become famous. And when you become famous, don't forget about me, okay? Let's do it together. Right, so Langmuir isotherms. This is Langmuir isotherm. And you don't need to worry about how Langmuir isotherm come out found. You don't need to remember. You don't need to know. I just tell you. The Langmuir isotherms is a more complicated expression that is valid for some systems over a wide range of the sorbate, partial pressure, or concentrations. So this is what we call Langmuir isotherm. Again, don't worry about this equation. I will give this equation to you when you have your final exam. But you need to know what is Xi over star stand for. What is Pi? What is A? What is KL? Okay? So you can use Pi or use Ci. It depends on gas phase or liquid phase. And good news is KL or KL prime are parameters determined by fitting the equations to the equilibrium data. So this is kind of what? This is not a theoretical mathematical modeling. This is kind of empirical modeling. That means that what? You have the experiment first, and you find out the mathematical equation. So this is what we call empirical equation. Okay, this is good news. So for example, if the system of carbon tetrachloride to the carbon, A will be 0.794, KL will be 0.096. That's it, at 34 Celsius. It can be a temperature range somewhere, something like this. So if this example show up in your final exam, I will give you A and KL. But don't forget what's Xi and Pi. Right, we have 10 minutes. I think we can finish this chapter. Right, so example 6.7-1 is a balance on adsorption processes. Right. Again, this is the example of air and carbon tetrachloride. Carbon tetrachloride, you don't want carbon tetrachloride in the air, so you want to put activated carbon to adsorb the carbon tetrachloride. So let's read the text first. A 50-liter tank contains air carbon tetrachloride mixture at 1 atm. Absolute. Okay. If this gauge, what's the absolute pressure? Anybody tell me? Anybody want to tell me? If I say this is at 2 atm gauge, so what's the absolute pressure? Yes. +1, right? Thank you. 0.1 point. 0.5. Okay, 0.5. Good. I'm happy. We have good interaction. Right. So if I say gauge, that means what? Absolute pressure will be +1. That means it will be 2 atm. Right. So it's at 34 Celsius and 30% relative saturation. Remember what is relative saturation? I want you to remember because it's very likely to be in your final exam. If I say relative humidity, you need to know the definition of the relative humidity. Okay, but anyway, in this case, I will tell you what's this. So the activated carbon is placed in, so there are so many carbon tetrachloride, and you want to put activated carbon is placed in the tank to adsorb carbon tetrachloride. Okay, the temperature of the tank maintained at 34. So this is what we call isotherm, right? 34 Celsius, and the clean air is continuously supplied to the tank through all the process to maintain the total pressure at 1 atm. So 1 atm we want to keep it as a constant. The pressure we want to keep it as a constant, and then temperature we want to keep it as a constant. And in this case, we want to reduce the amount of the carbon tetrachloride in the gas phase. Okay, so the process may be shown schematically as showing like this. So in the very beginning, we have volume which is 50 liter. This is 50 liter, right? And then temperature is 34, and the pressure is 1 atm. And then 30% relatively saturated. Okay, so you have 30% of the carbon tetrachloride in this system. Right, so what you don't know in this case is the total amount of the gas in this system. Right, you don't know the amount of air and carbon tetrachloride, you don't know. And also you don't know is the more fraction of the carbon tetrachloride. You just know the relative saturation. So this is kind of specification for you to achieve or for you to attain the Y0. Y0 is molar fraction of carbon tetrachloride in this chamber. So this is the initial state, right? This is initial state. And you already know carbon tetrachloride is too much, so I put activated carbon in this system. So carbon tetrachloride will be absorbed on the surface. So the carbon tetrachloride will be less in the air, right? So the question is calculate the minimum amount of the activated carbon needed. So you can put a lot, you can put so much, you can put a very little, or you can put something like this. But you want to reduce the amount of carbon tetrachloride to a certain level, which is need to be reduced the carbon tetrachloride mole fraction in the gas phase to be 0.001 from Y0 to become 0.001. Okay, why? Because you have activated carbon here. Okay, neglect the value of the activated carbon. So forget about the size of this carbon. Okay, and then absorb carbon tetrachloride. What would the actual amount? Okay, forget about this sentence. So the thing is that you want to put what's the weight of the activated carbon required in this system in order to achieve the concentration of carbon tetrachloride to become 0.001. Okay, so now let's write down the final stage. Value is 50, right? Because forget about the size of this one. And temperature is 34 because this is called isotherm, right? Isotherm. We keep the temperature as constant. And pressure is 1. You might say, wow, Professor, something wrong because the carbon tetrachloride absorbed on the surface, the pressure will reduce. But here, we say we keep on introduce the fresh, clean air into this system to make it become 1 atm. So anyway, pressure will be 1. And the total will be the same, right? Amount will be the same. And then this is Y0 will become Y tetrachloride 0.001. Okay? And then unknown is MC. Right? C stands for carbon, activated carbon, N sub C. So you need to find out what's the amount of the MC, amount of the activated carbon. Okay? So how can we do that? And also want to find out the amount of the absorbed carbon tetrachloride absorbed on the surface of the carbon, activated carbon. Okay, so how can we do that? The important thing is find out Y0 and MAADS, right? So you have the isotherm Langmuir isotherms. So you have an equation. So let's find out Y0. So in the very beginning, you need to know the definition of the relative humidity or relatively concentration, which is Pi divided by Pi star, function of T. This I is carbon tetrachloride. So SR will be 30, right? Which is 0.3% equal to P, the partial pressure divided by saturated partial pressure of the carbon tetrachloride at 34 Celsius. So how can we get this? How can we get this? Anton equation, find in the textbook, right? Anton equation. So you got A, B, C, and this T will be 34. So you got P star, this one. So as a result, you find out the partial pressure. You find the partial pressure of this one, and this one will be what? The partial pressure will be mole fraction times total pressure. Remember, this is what we call Dalton's law. Remember, Dalton's law. From the PC0 to Y0 P dot P. So you got the total pressure, and then you have this one according to this one. So you can get Y0. So Y0 will be 0.0667. So from 0.0667 to become 0.001. How much amount of the activated carbon required? Okay, so initial state, final state. So you know the amount of the, so for this, so the mass of absorption will be this one, Y0 minus Y final, right? So you have this one and equal to what? M and total molecular, total moles. So this is the what? This is the moles of the carbon tetrachloride adsorbed, right? And but you need, this is moles, but you need to know the weight. So you have to times what? Molecular weight of the carbon tetrachloride, right? From mole times molecular weight will become weight, the mass of the adsorbed carbon mass of the carbon tetrachloride adsorbed on the carbon activated carbon. Okay. So what is total? Total you can get what? Total is PV equal to nRT. You have value, temperature, and pressure, so you know the total, no problem. So you got M ADS. Okay, so you get this. So now you have Y0 and M ADS. So now it's MC. So what's the amount of MC? Langmuir. If I give you the Langmuir here, and I give you the A, constant of A, constant of KL, you put the number in, bingo, you got this. Okay? So please, so MC will be 370 grams carbon. This is not difficult as long as you know this equation and you know the constants. So please go home and practice by yourself. Okay, I think I run out of time today, so